So good morning, everyone. My day started at 6, but I'm late anyway. So in the end of my talk, I will sweat anyways, because we have a hardware demo of motion prediction with acceleration and rotation rates. And we try to predict with machine learning whether the device is running, sitting, walking, or going by bike. Everybody of you who have an iPhone got, since the last version, the M7 motion processor and now the M8 motion processor. So your iPhone or probably your Android smartphone is doing this all the time, measuring acceleration and rotation rate and predicting if you are running, sitting, or going by bike. So most important thing first, hello Greta, because my daughter is at home and I had my job this morning. So short introduction video, 3 seconds or so. So the device, I will show you in the end of this talk, in your pocket, and we will predict which activity the person or the device is doing. So I don't know if everybody of you are on Twitter and saw I posted the link to code and stuff and everything right from the bus. Means 20 minutes ago. So the code is on GitHub and you can download it afterwards. It's no basic machine learning talk, so we are not going into details how the algorithms work. It's all about feature engineering. You know, the algorithms are in talks all over the world. You can look at YouTube. There are very good tutorials. So today we'll talk about feature calculation to estimate what happens with this device. So let's dive into it. I prepared a log file named activitydata.csv. I created a file with my smartphone. There's a sensor log app and I put it in my pocket, started logging acceleration and rotation rates and dumped it into log files. And now I have the labeled activities. I choose 4 activities and log them with 50 Hertz. That's actually a good measurement rate. So here you will see the data. The devices are 6 degrees of freedom in inertial measurement units. That means you have acceleration in 3 directions and you have rotation rates around these 3 axes. That's in your smartphone. That's on this device. It's from Tinkerforge, German company. They sell you a very good IMU and master brick to connect via USB.
Did you label the data while you were?
Yes. I started logging, put the smartphone in my pocket and drove with my bike. Afterwards, I labeled the file biking. So I have these motion data with labeled activities. So it's supervised learning. We have some description for everything. Not very discriminative, but the first feature I want to introduce is the absolute acceleration. That means you don't need to get the orientation of the device. It doesn't matter in which orientation the device is, in your pocket or in your bag or on the bike. You have this simple calculation. Take all 3 accelerations and calculate the absolute acceleration. That's what I'm doing here. I'm calculating the absolute acceleration of the data. And here's our first feature, or hopefully a good feature. You see, while sitting, all the devices in your pockets have absolute accelerations like this. That means 1g, that's the acceleration towards the Earth. The gravity, it's 1g. So while sitting, you have an absolute acceleration of 1g. While walking, it's a little bit messy, and while running, when you run, you have a high variance of the absolute acceleration. So maybe, and I know it's true, so maybe it's a good feature to estimate which of the 4 activities the device is doing. So we calculate the difference of max-min with rolling max and rolling min. It's Pandas. I'm using Pandas most of the time. So rolling max minus rolling min of the absolute acceleration. And you can think about it. You have a hull curve on top and on bottom, and the difference between is the difference of the absolute acceleration. So that's the first feature. It looks like this. So while sitting, it's nearly 0. Walking, running, nearly 3. And while biking, it's 1 something. So if we take a look at these features in scatterplot, it's looking like this. So here you have sitting means absolute acceleration of 1g, and nearly no difference, no variance of the acceleration. And the green one is running. But walking and biking is in the middle, and you can't separate running and walking with this feature. So we need a second feature, and this is the rotation rate of the device. The rotation rate is looking like this. Rotation rate means how fast the device is turned. So no turning, no rotation rate. Fast turning, high rotation rate. So if you take a look at these values while walking, it's looking like this, and while biking, it's looking like this. So you see, if you have your device in your pocket and moving your leg periodically, so you have to bike, then you see a periodic movement of the rotation rate. So, and engineers in this room know what to do with periodic signals. You have the FFT algorithm. You can throw a value in and get a frequency back. So the FFT algorithm animated. So if you don't understand the FFT, this is the animation of it. You have a signal. These are 2 mixed signals. The green one is the resulting. And think about you're looking from the side. So you have the imaginary plane and look from the side, and then you have the amplitude and the frequency. And this is what the FFT algorithm is doing. If you need code for FFT, here it is. And we fire this FFT algorithm on the whole data set, on the whole rotation rates, and you see while biking, you have here something 2 or 3 hertz, means 2 or 3 times per second, a high rotation rate, and while walking, it's not the case. So that's the second and also most important feature to separate all activities. And now we've done that. Oh, you see, this is walking, the FFT amplitude peak in radians per second, so the rotation rates. Here you have walking, and that's biking. So now we come to the machine learning part. That's where you guys are more professional. But I did my best to work out how to estimate the activities. If you plot a scatter of our just two features, it's like I told, the difference of absolute acceleration and the FFT amplitude peak. You see, actually these are two colors. Not on this beamer, but on my laptop, these are 2 colors. It's probably biking, and that's probably walking. So you see 4 clusters of features for 4 different activities. Looks like an easy one. I separated in labels and training data and trained with, I think, trained with 80%, so tested with 20. And I'm using an SVC with a linear kernel. You can do more magic, but that's all I understand. And I know in every machine learning talk, there is the rule, if the accuracy score is 100%, you did something wrong. I don't know if I don't know if I did something wrong. I mean, the features are pretty discriminative, and I probably understand the SVC algorithm, and so the accuracy score is 100%, at least for my labeled data. We will see the real world example is not 100% accuracy score, but if I have to present this to my boss, it's a pretty good example. You don't see the description borders, the decision bounders. That's because this is too. Here they are. So you see the SVC figured out some decision boundaries for every activity. So we developed a machine learning algorithm to separate activities based on our features. So let's save it and let's try a real example. I have here this file Tinker live classification, Tinker because that's a TinkerForge sensor, and live because I'm now running as far as I can. And hopefully it will show you. First, let's take a look at it. So, like I said, the TinkerForge EMU, I'm connecting to it with some code. I'm loading the classifier we developed. I calculate the features from the raw sensor data. The both features, here is the FFT amplitude peak and here's the X acceleration max min diff. So two features, and I collect sensor data until I got 1 second. 1 second of signals, because for the FFT you need a window size, a specific window size to calculate the FFT. So I'm waiting 1 second, then I have at 10 milliseconds sample rate, I have enough values to calculate the FFT. And after that, I'm firing everything through the predict step. You see classifier, that's the one I loaded, predict with these both features. So, any questions so far? Because now I'm trying to figure out a window. So, right. So it's connecting to this device, and you see the device is sitting, and hopefully now. So I have to put it in my pocket, because that's where I measured the examples. So now you see the accuracy score isn't 100%, but I think sitting or standing. Yeah, that's, yeah, in your face. Wait a second. Better? So while I'm sitting or standing, it should say sitting or standing. While I'm walking, it will predict I'm walking. While I am running, it hopefully predict I ran harder last time. Last time it was a harder running. Other shoes, other ground. Yeah, no running this time, because I'm actually not running, so it's pretty smart. So the last one is biking. You see the movement of my leg. is estimated as spiking. So not really 100%, but if you look at your Apple device in health, it doesn't detect every action you're doing, but nearly every action is separated from each other. So I think a lot of questions, because it's engineering and not data science, but these two disciplines are matching now because engineers trying data science, it's like me, and data scientists got jobs from real world problems, not just computer problems. So questions so far?
Is there any, I don't know what this IMU is doing, but usually there's like a Kalman filter applied to this sort of sensor data.
Yes.
Are you using this in the hardware, or
These TinkerForge guys did a great job. They implemented a filter performing better than a Kalman filter, and you get the orientation of the device filtered. So not the rotation rates or the acceleration, but if you need the orientation of the device, it's filtered through a filter. It's not a Kalman filter, but something like that, yes. And it's implemented on hardware. You can get it via API. So TinkerForge does a good job on that.
What do you do?
What?
Obviously, you know it when you're sitting, all right?
Yes.
So what do you actually do?
If you are on a healthcare site and you want to know if a person got a lone living person got a problem, so walking, then sitting or laying on the ground, no movement, then you have to estimate the state of the person. So that's the easy part. Separate if your grandma is biking, or running, or walking, or sitting. And the harder part is detect if the person is laying on the ground or sleeping or falling to the ground, something like that.
Okay.
So these are only 4 states. You can imagine you have some more states to predict in real life.
How did you get the window size of 1 second?
How fast can you change your activity as a human?
Yeah.
And I thought, okay, the FFT algorithm gets better if the window size is longer. So if you just have 1.0 or 1.01 second, then you just have 10 values, and you have to calculate the FFT with just 10 values. It's probably inaccurate then.
But it could have been like 2 seconds.
For sure. But
it was like you just tried it and it worked.
Empirically chosen. Like, yes. That's right.
Yeah.
So it figured out the 1 second window size is a very good delta time for activity change for humans, because if from biking to walking it takes 1 or 2 seconds, and so you don't need this more often. I can reduce it to 1.0 seconds, then it's but it's no information gain. Yeah.
If you have it on your wrist or somewhere else, it's probably more difficult. Did you test it, or if you can still get the states?
I think Apple got the states from the iPhone and your health data from the watch. So I don't think that they can estimate everything from your wrist, but I think there are good features to estimate. You have to move your arms, so you can estimate some states from wrist. And as far as I know, healthcare devices are on don't know the word. Chest on your chest or on your wrist, and they try to figure out what your activity is, or are you laying, sitting, something like that. So it's possible, but I think with other features or some more features. We just had 2.
How many persons were involved by collecting data?
Just me.
So that's eventually why it was so clear separation then.
Yes. What?
Clear separation in the groups that or labels.
Yes, because it's it's the easy part. I just took the clear part. You know, if you go on by bike and jumping over rocks and something like that, you have different features. So it's not this easy for off-road biking or something like that. So I made it easy that the accuracy score is 100%.
Also no traffic lights.
Yeah. No braking, no acceleration while biking. I think.
How do you put the labels there?
I started logging,
Yeah.
drove bike, 5 minutes, stopped logging, and named the file
You
biking.
were like looking at your watch and saying like what, from 11 to 11:05
No.
or whatever I was biking, and then afterwards.
No, I logged 4 different log files. I started logging, drove bike, stopped, saved the file named biking, then started logging, running, saved the file running. So the labels are, and you can see how I made the data. You have here in the data set the prep data IPython notebook, and there you can see the magic. I read all log files and got the name from the label for the activity from the file name. So.
Thank you. No more questions. Thanks, Paul.